Welcome. Let me briefly say something about zeta functions. There are various ways how one can define zeta function. The mother of all zeta function, of course, is the Riemann zeta function. It's a geometric zeta function which is defined by the Dirac operator on the circle. And there we have explicit eigenvalues. The eigenvalues are n, and so we can write down the zeta function, the spectral zeta function, which also can be written down in general. If you have a simplicial complex and you have a Laplacian, you have either the Hodge Laplacian or you have the connection Laplacian, you can write down spectral zeta functions. Here there's a nice kind of symmetry. There is a functional equation. This doesn't happen here. With one exception, I found here in 2018 that if you take the connection zeta function, which is very nice, L is invertible, so we don't have to cut away the zero, right? Here you cut away the zero eigenvalue, and also here you cut away the zero eigenvalues. So we don't have, that doesn't make sense to look at zero eigenvalue. It doesn't make sense also to look at negative eigenvalues. That's the reason why I look here also at the square, and then just take S half, which kind of takes the square root. You need to have positive numbers so that in the complex this makes sense. So this is the zeta function we can look at. So we take the square of the eigenvalues, and so we have the square of the eigenvalues of L. And then in the one-dimensional case, there is a functional equation. So the spectrum is symmetric with respect to S equal to 0 here. And that's not so easy, and I would really love to have a simple proof for that. It's kind of a symplectic structure which you find in this connection matrix, at least in the one-dimensional case. If lambda is an eigenvalue, then 1 over lambda is an eigenvalue, which is pretty cool. And there is another relation between this world, or between the Dirac world and the connection world in the one-dimensional case. That's called the hydrogen identity. L minus L minus 1 is the signless Hodge Laplacian, but that's only true in the one-dimensional case. Now, of course, if you have the zeta function here, the famous problem is to find the roots of the zeta function, and they are believed to be on the line real of S is equal to 1/2. Actually, I think that's wrong, but that's the most difficult open problem currently in mathematics. I was interested here in the case of the cyclic graph, because this is kind of a discrete circle. You have then explicit eigenvalues, which is nice. So you have an entire function. So all this for every n, these are entire functions, and you can study what are the roots of this zeta function. So I looked at that, and it was quite a hard analysis and not so easy proof to show that that these roots converge closer and closer to the real S is equal to 1/2. It's a very slow convergence. And I have in that paper, 2013, I have also lots of illustrations which show that. In this case, in the connection zeta case, it's easier to analyze, so because we have this symmetry, and also here the roots of the zeta function converge to the axis real of S is equal to 0. So there are explicit formulas for the limiting zeta function. But I still don't understand what really the structure of these roots is, whether there are gaps in this, for example, in the limit when the barycentric limit. You can look at the barycentric limit in any dimension, but in the high dimensional case you don't have the functional equation, and so the spectrum is, completely unexplored. What happens there in the barycentric limit. Yeah, that's what I wanted to say today.